So I want to speak on the difference between the two. Allow me, I will sit down. I want to speak on the difference between the two different embedding methods, which are currently available for embedding graphs, finite metric spaces, into Banach spaces. So I guess I felt the need to start with the formal definition of distortion, which I think everybody knows. You might notice that I wrote it, for me, X always will be the Banach space, so I wrote it without this special scaling factor in between. So let me say a few words about the classical embedding method that was available for many years, first used by Bourgain in 1986 and later used by Johnson and Schechtman in 2009 to characterize non-superreflexive spaces by embedding particular families of graphs into those spaces. So the result that was at the base of that method is the very classical result. I wrote here a long list of work where that result emerged partially simultaneously. It's a classical characterization of not reflexive spaces. That a space is not reflexive if not only if there exists some non-zero number between 0 and 1 and a sequence which is fine. So that any finitely supported scalar sequence, we have this inequality. So let me show it on the next slide. We actually have, as I say, as everybody knows, this is a very classical result. This norm is the standard L1 norm that we always use. This norm is what we call a summing norm, right? So this is kind of the factorization between L1 and the summing norm. So if we have such a sequence, how does the embedding go? Well, we try to take our metric space and we put it into C00, which denotes for me a space of finitely supported sequences. And for every u and v in the metric space, we want the map to be such that the L1 norm is below the distance and the summing norm, which in principle is always not bigger than the L1 norm, but it is bounded above by this. So then if we have the sequence, like in the characterization of non-reflexive spaces, we can define our map to be using this sequence from the previous theorem and taking the coefficients of this f of u, we produce the embedding, right? And this is the right embedding. This is the known method of embedding, which through this simple computation that I am not going to read out loud, this works. So this was the method used by Bourgain for embedding trees, and it was used by Johnson and Schechtman for embedding binary diamonds into non-superreflexive spaces. So I would refer to this method as a factorization method. Right, so recently, Mikhail Ostrovskii and I made the same mistake as Professor Fonf made. It was written on the original slide, but this whole talk is based on a joint work with Mikhail Ostrovskii. I apologize for not saying it out loud from the beginning. So we developed a new method of constructing embeddings into non-superreflexive spaces. And we use that method to show that finitely branching diamonds, I will later define what it is formally, but It's kind of like a diamond, except we have 50 branches instead of 2, or 50 million branches, however many we like. And so we proved that they can be embedded with the distortion independent of the number of branches. So this method is based on the theory of equal-signs-additive basic sequences, which also characterizes reflexive spaces. And if time permits, I will outline that method later. My first goal here, the main goal of this talk, is to prove that indeed the previous method does not work for this class of graphs, that they could not have been embedded using the factorization method, that the new method was necessary. So what I want to prove is the following theorem. So if I denote by this symbol a diamond which has k branches and n levels, and the formal definition in a picture in a second. And the proof that we have is that imagine that we embedded this metric space into C00 in a way that would lead to the embedding by factorization method. And then we prove that that means that there is a bound on the number of branches that it could allow. That bound depends only on this C. All right, so what I want to note first is that what this is, I am not saying that if I say stick to 50 branching diamonds, that they could not be embedded using the factorization method. I don't know if they can or cannot. But all I am saying is that if any k branching diamond is embedded using the factorization method, then this constant C here will have to depend on the number of branches. And that number of branches will have to go to, and that constant C will have to go to infinity as the number of branches increase. In fact, yeah, that's what I just said. So in fact, we don't even know if C of 3 exists or not. C of 2 does exist, it follows from the work of Johnson and Schechtman, but C of 3, we don't know. So the definition of the diamond. So the diamond is this fractal-like structure. I guess the picture is better than this writing. So this graph over here, this is what we call diamond of the first generation with k branches. This is really the complete bipartite graph with a 2 and a k. Right, so then what do we do next? Well, what we do next is we replace every edge by a copy of the same graph. And my graphs are going to be unweighted, so every edge has length 1 in all pictures, right? So this is an illustration of the level 2. Well, I wrote 2k, but k is 3 on this picture. All right, so those are the kind of graphs we will be talking about. So the proof follows 3 steps, right? So first we imagine that we have an embedding, and the first step is by now a very classical step, which is that we can embed it in such a that if I have an embedding for any n, for any number of levels, then I can find, which is with some bounded distortion here, which does not depend on n, then we will be able to find an embedding so that this one copy is vertically faithful, is the terminology introduced by Mendel and Naur, right? So this is, which means that when I am mapping this, in the true graph, the distance from the bottom vertex to the middle vertex is exactly 1/2 of the distance from the bottom vertex to the top vertex. And I want it like that. I wrote here approximately there will be some epsilons. I don't want to bother you with the epsilons, right? So that is a method which goes back to Mateuszek. The first published in English paper is 1999. He says that it actually goes back to the paper not published in English in 1989. And it was used by Lee and Raghavendra in 2010 and then Mendel and Naor in 2013. And this is the, by now, very standard self-improvement argument, or Lee and Raghavendra refer to it as coarse differentiation, which was introduced by Eskin, Fisher, and White in 2006. And it's also used by Chigger and Kleiner. And so this is a very standard step. So the second step is also very simple. So we have this embedding, which is already such that when I restrict my attention to a selected one diamond, then it is vertically faithful. And we want to improve this embedding further in such a way that the top vertex is mapped to a vector whose every coordinate is either 1 or -1. Right, in the embedding of Johnson and Schechtman, the top vertex went onto a vector which contained just ones. So here we are a little bit more liberal with it. We allow ±1s, but not anything else. This is possible to achieve. And the vertices in the middle, the metric midpoints, they are mapped onto elements whose coordinate is always between, the modulus of the coordinate is always in between 0 and 1, and its sign agrees with the coordinate of the top vertex on that coordinate. So what we achieve is, and this is, I am not going to show too much detail about this, but what we achieve, and it's really very simple computation, we achieve, so here when I'm writing what we achieve, I even ignore the top vertex, I ignore the bottom vertex, I just talk about those middle vertices, right? So the middle vertices, first of all, they have, each of them has finite support, and totality of them has a finite support. The modulus, so M here is a fixed coordinate, and the I and J are the different vertices. They will have the same sign, because they have the same sign as the coordinate of the top vertex, and that value will be a number of modulus less than 1, so in particular, the difference between less than 1. And then, and this is the crucial thing from this method, the summing norm of the difference of those vertices, they are separated, right? Because this is a bilipschitz image of the diamond. So those are the midpoints, which are separated in the graph, and they are separated in my image by assumption. All right, so we achieve such points. And then the final step, the main step of this proof, is that imagine that I have points, I rewrote it because I can never remember when we go from one slide to the next. So for your convenience, it's written here again. Imagine we have the sequence like I just described. Then it's a finite set of points. Then the number of those points has a bound, which depends only on alpha, with this alpha kind of changed from C to alpha. It's a fixed number. All right, so how do we prove this? So the way to prove this, uses Ramsey theorem. But let me go quickly over this proof. Sorry, that's not what I meant to do. The proof is slightly technical, but I am decided to do it in pictures. So hopefully this will be readable. So the first thing we do is like, I have those ij in my set of midpoints, and I will denote by Rij the smallest index which witnesses the fact that the summing norm of the distance is at least alpha n. Right? So such things certainly has to exist, and I am taking the smallest of them. Right? And since all those differences have modulus less than 1, so I certainly achieve this upper estimate at the same time. Right, so what we are going to prove, first we are going to prove is that these numbers Rij, they cannot stay together. They have to keep moving forward. And there has to be the difference between their size, and that distance between them is proportional to the n, right? Because the whole point of this whole computation here is that we don't restrict by the number of coordinates onto which we put it. This n can be arbitrarily large. It doesn't depend on n, it only depends on, I mean, the bound k of alpha doesn't depend on n. So this will be the first thing we will prove, that those numbers that are defined here are separated. So then what we are going to prove after that is that if we imagine that every time I have a triple of point that generates a triple of numbers ijl, k is reserved. So then that generates a triple of these indices up there. And if we knew that, say, it's always attained at this RJL, which is the largest pair, so then we would be able to say, oh, so they keep growing. And as I move to the next pair, it keeps growing, and eventually I'm supposed to reach my k, so I can only make a finite number of steps. And which will lead to this bound on the size of k. I'm going to show that in a slightly more detail. So it is important to us that they stay either it is this one, or that one, kind of consistently for all pairs. So this is where the Ramsey theorem comes. We will color our triples depending on which one is the biggest index, right? So that is the general outline. Before I am ready for this coloring, let me first prove the first claim, that indeed if I have any three numbers, and I have those three triples, and I take the biggest of them and subtract the smallest of them, then the distance is proportional to n, proportional with the constant of proportionality alpha over 4, which is fixed. Right, so how do I do this? Well, so this is a computation that I do want to show. So if I have, so first I introduce this notation that I fix Rij. So I have my three numbers, ijl. I fix Rij, and I denote T of I, T of j, T of l to be the sum up to Rij. For example, this. I just go to this one sum. And so then this norm Zi minus Zj is precisely, the summing norm is precisely Ti, tau I minus tau j, right, the absolute value. And by assumption, that is the number which witnessed the summing norm distance between those two places, those 2 points. So, so I want to say that the other point cannot be together. So why is that so? Well, when we have this, we have the options, right? So we have those 2 points which are separated by a number slightly bigger than alpha n. And then we have 2 options. Either we have tau l minus tau I smaller than tau l minus tau j, or further, meaning it is, it's closer to one of them, say closer to tau I. right? So then I want to consider first case. First case is here on this diagram, that my tau L is within that blue shaded interval, meaning it is within the distance alpha n plus 1 over 2 of tau I, right? So if it is there, right, this is case 1, so that means that I have this sum from 1 to Rij. That sum is less than this number. However, we do know that if I summed I and L all the way to RIL, that is the index which witnesses the summing norm distance, meaning this index, this value will be alpha n, at least. And since each of those summands has modulus less than 1, less or equal than 1, that means I had to have enough summands. When I go from this number to that number, right? So here I am using this symbol sum like if it was an integral, meaning if I go forward, I take it with a plus, and if I go backwards, I take it with a minus. And so I have this sum here. Each term has modulus less or equal than 1. The sum is this much. That means the number of terms had to be at least this much. I mean, that's really all it is. So that's the conclusion, that this number of terms, which is greater or equal than this, has to be, and this is a difference between alpha n minus that number, right? Which is greater or equal than alpha n over 4, because I am really not interested in small n's. All right. So as I keep moving forward, the second case is very similar, right? Rather than my tau L being in the blue interval, it's in a yellow interval away from T of I, right? But again, this is that same principle that in that case, if it is in this yellow interval, that means that its distance from the further away point has to be the distance between the 2 points plus this alpha n over 2, which makes it around 3 alpha n over 2, right? So this is again the same exact behavior, that when I sum it up to this index, I obtain a large number. When I sum it to this index, this was the first place where the summing norm was met, so it exceeded alpha n, but not exceeded it by more than 1. So it is at most this much. So again, the difference between those 2 points, those 2 values, is about alpha n over 2. And again, all my steps are of size 1, so I had to have a large number of steps, right? So, which is written over there and over here again, right? So that finishes the proof of the lemma that those values cannot stay together. They have to move forward. Right, this lemma which is repeated over here. All right, so what is the final step of the proof? The final step of the proof is that I want to color my triples into colors, right? So there is this complicated description here. The first one is easy, right? The red is if this is the one. And here there's this condition, you know, in case, which really means this one but not red, right? And then this one but not one of the previous colors. So what we want to prove, so the first thing we know is by Ramsey theorem, we certainly can guarantee that all the triples will be of my fixed color. And we are going to show that the number of triples, no matter which color was selected, is bounded by something that depends only on alpha. And those colors are not exactly symmetric, so we will consider them separately. Right, so let's consider the first case when the colors are red, all the triples are red, which means the largest index is the largest. So in particular, so we do it inductively. First, we look at the triple 1, 2, 3, right? Since they are red, the largest index is on that red, indicated in red, 2, 3. All the previous ones are, of course, greater than alpha n, because the definition of Rij is always, I am summing until I reached at least alpha n, and I am summing things which are of norm 1. So at most 1, so I need at least alpha n, and then plus that step, which is the separation, the largest minus the smallest. Both of the previous ones were bigger than alpha n. This one is biggest, so it's bigger than the smallest of them, all right? So as we do that, did it matter that I had over here number 3? Well, it didn't matter at all. If I had a pair, a triple, 1, 2, and t, where t is some number bigger than 3, it would be same exact reasoning, right? This is a red case, so the 2t is the biggest triple, the biggest pair in the triple, so I get same exact estimate for this. All right, so now I go to the next step. So those were the triples that started at 1. If I have triples that start at 2, then I have 2, 3, and then 2t. I already know that 2, 3 is at least of this size. I know that 2t is also of this size, and I know that 3t is bigger than both of, it's bigger than both of them. It's bigger than the smaller one of them plus alpha n over 4, which leads to this inequality, right? So as we keep going like this, until we reach the last stage, we will obtain that the last pair has to be at least alpha n plus s minus 2 times alpha n over 4, right? But we, of course, know that that number has to be less or equal than n, because I only have n coordinates to begin with, right? So, which is written over here, right? All my points live on coordinates from 1 to n. So we prove that if all the coordinates are red, then cardinality of B, which is here denoted by S, will be smaller or equal than 4 divided by alpha, because n cancels, right? If the triples were blue, blue means that the smallest is the smallest 2 indices reach the maximum. It's the same thing, I will just go down instead of up. If the ones are green, it's very similar but slightly different. I need to start in the middle, right? So if I start in the middle, so here the point is not so much where they are, but how many are in between, right? So if I am having one point in between, then on my pair TU and UW, the TW is the biggest pair, so it needs to be bigger than the minimum of the others, which is at least alpha n, plus this step coming from the lemma, right? And then if I had more than one here in between, there would be the same thing. Well, it keeps adding. If I have extra pairs, right? So because here, I guess as long as it is greater than 1, right? I have at least 1. They will be separated like this. If I have separation here, by induction, I get more and more of those added steps. So at the end, right, every time I double the number of steps, I will get this, right? So in essence, and to what is my most separated point, when I take triple which has 1 and the s in it, and those things in between, right? So how many times do I get? Well, R1 to S will be greater or equal, and this coefficient here, we compute it to be log base 2 of S plus 2 times the size of our step. This is how many steps we needed, right? So we also obtain that in this green case we have a more restrictive inequality. Cardinality of B, I guess, can be larger. So then when we combine all of this together with Ramsey's theorem, we know that we can that K of alpha is at most the Ramsey number. So this those 3 and 3, one indicates that we are dealing with triples, and one indicates that we are dealing with 3 colors, right? So, so this is a finite number. I don't know the exact value of this number. Right, so not unique in that property, I think. So, so this is what we proved, right? This is the end of this proof that if we did have an embedding with this that satisfies this inequality, which is like the start of the factorization method embedding, then the number of branches is restricted. And what I want to say is that really what we proved is that when you embed this D1K, this little diamond, and you try to embed it vertically faithfully with this property, that's what cannot happen. So this doesn't only work for diamonds in general, but it works for, what were the names? The parasol graphs, the Laakso graphs, the every kind of multi-branching graph that is built. It doesn't even need to be, I mean, it needs to be sufficiently regular so that I can conclude that I have this, this vertically faithful copy of a D1K in it, which all these graphs will have it. So this is a general statement for all of them. This is the first branching. So everything that branches K times cannot be embedded this way with the uniform distortion. I don't know, I guess I should have been stopping and asking if there are questions, right? Since I did go over the full detail of the proof. Maybe this is a good time to ask for questions? No questions, all right? So, time permits. So we are going, so what I want to do next, very briefly, and without giving full formulas because I don't think they would be readable in this kind of setting, but I want to outline by pictures of how the embedding method works, because we did embed all the multi-branching diamonds into every non-superreflexive space. And we also, in the paper, we included the construction for embeddings of the multi-branching Laakso graphs. And more recently, Andrew Swift, who is here, developed a new method of coding of such multi-branching graphs, which includes all the graphs at once and embedding them into the non-superreflexive, all non-superreflexive spaces. So this method relies on a different characterization of reflexivity, which is the characterization due to Brunel and Sucheston from the 70s, that if a space is non-superreflexive, there exists a Banach space E with an ESA, oops, this is the first time I'm using ESA. ESA basis, meaning equal sign additive basis. So what do I mean by that? Here's the definition. It is equal sign additive, so meaning when I have my sequence, if the two neighboring coordinates have the same sign, that's why they call it equal sign. If those two, they have same sign, then we can add them for free without changing the norm. So this happens, for example, in the L1 norm, right? If the two neighboring coordinates have the same sign, I can add them and the modulus of is not going to change. If I have a summing norm, it's also satisfied, because if I have two neighboring coordinates of the same sign, this is not going to change the norm. So they introduced those three definitions.
Is there a minus? This plus, should it be a minus or something? Because I don't see the difference between the two terms.
No, see here on the part one, I am saying that the signs are equal of those two. And here I am not saying anything, so they are whatever.
Okay, yeah.
So if they happen to be the same sign, it's equal. So effectively, the second one is talking about the case when the signs are opposite. But the way they stated it, like, you know, general. In general, it is less or equal. But if the signs are equal, then it's equal. And then invariant under spreading, meaning that doesn't matter if I push my coordinates forward somewhat. And what they proved right away is that this equal sign additive condition, the first condition, is equivalent to the two other conditions. So that's probably why they didn't state it with any extra assumption, right? It's just you make an assumption that when you add two neighboring coordinates, you don't increase the norm. And then you're allowed to spread, and those two are equivalent. All right, so which is a very cute little lemma, actually. Okay, so we have, so I want to describe an embedding of this D1K, right? This is our crucial embedding, right? So the embedding I'm going to describe is actually going to be vertically exactly faithful, not even with any epsilon. Because I am having the exact ESA basis. So the elements I will work with will have coordinates 0 and plus minus 1. I will restrict my attention to only such elements. And instead of plus 1, I will write plus, and instead of minus 1, I will write minus. And if there is a bunch of zeros, I will not write them, as is traditional, right? So I will write this symbol instead of such a long symbol to mean the same thing. Right, so what I want to kind of notice here is when I look at this element, which is E1 plus E2 minus E3 minus E4, right? So that element it actually has many metric midpoints, but in particular has two metric midpoints, which I like, right? So those 2 points, this and this, are both metric midpoints of this point. Yes?
You need to explain what you mean by midpoint of a point.
Okay, so thank you. So what I mean is a point which is halfway between this point and a 0. And when I say metric midpoint, that means I don't draw any straight lines, I just count distances. Meaning I will be talking about, what I am saying is precisely what is written here. The distance from this point to the other one equals the norm of the top one. And this is simply because this minus that equals this. I am not using any properties of anything here, I'm just subtracting. And then here I am using here I am using the properties of the basis. That, what property did I use? I used the property that plus minus, I added them together and I got a 0. And then I pushed it so I got an element 0, 0, plus minus, and then I pushed it around so that it sits in the middle. Right? So by the SA property, I didn't increase the norm by doing this. And again, because I can push my zeros around any way I like, so this is the same exact norm. This is the IS property. And then this is 1/2 of this because here I can use the ESA property. When I have 1 and 1, I can replace it by 2. And minus, minus, I can replace it by minus 2. And certainly, I mean, it's a norm, I can factor 2 out. So this actually equals this. So which I guess is a lot stronger what I said over here, right? So this proves that those are midpoints, right? The distance from 0 to this location is the same as the distance from 0 to that second point, and it is equal exactly 1/2 as a distance from 0 to this, what I will be using as a top vertex. Right? So what I am saying is, we embedded the diamond with the two-branching diamond into the space. This actually, if I forget about those minuses and just pay attention to the first half of this picture, this is exactly the embedding of Johnson and Schechtman onto the factorization method, right, of the two-branching diamond. But the thing here is that we are going to be able to repeat this and make it for, first of all, more branches, and second of all, more height. So first, how do I make more branches? Instead of 2, I want k branches, where k is... so one thing that I want you to notice here, from this equation here, it follows that this is exactly vertically faithful. This is exact 1/2 of the entire distance. All right, so how do we introduce more branches? So for the top, instead of taking one point like this, we put this vertical bar is for picture purposes much more than anything else. It doesn't mean anything other than grouping it into groups of 4. So we have this one group of 4, another group of 4, big bunch of groups of 4, which will be followed at the end by bunches of zeros. And each of those groups I call blocks. So if I want to embed a diamond which has k branches, I will put 2 to the power k blocks like that over here. That will be my top vertex. So what we saw on the previous picture is that each of those blocks had 2 very nice metric midpoints which were far apart. And so now I am going to multiply those midpoints, because in each block I will randomly select one of those 2 favorite midpoints, right? And if I use a Rademacher to select them independently, I am going to get a big bunch of midpoints where mi will have this randomly selected block in each, midpoint in each block. So the norm of the midpoint will be precisely 1/2 of the top vertex, and the distance between them will be at least 1/4, because in half of the blocks they will cancel out. In the other half, my ESA property counts it for me and gives me this estimate. So I have as many as I wanted midpoints. And this is an embedding which is vertically exactly faithful, the one that I said is impossible if I try to do it using the factorization method. Okay, so I have 1 minute, 2 minutes left. So as I said, this can be iterated. It does get technical. What do we do? I do have a picture. So the top will be similar to this, but we will have more blocks, and we will have bigger blocks, right? So what do I mean? So if I want to embed 2k, right? This is a talk. I am not going to go into full generality here. So I just doubled the size of the block. And as I want nk, I will further increase the size of the block. All right, so now when I have such a block, so first, what are the good midpoints of this block? Well, this is the exact repetition of what we did in a smaller block, except I doubled the number of entries, right? So those are still midpoints. They are still separated. And then each of them really is a copy of the original block. Each of them, again, has nice separated midpoints. And they are listed here. There are 4 of them, right? So now, and then I notice that this item, this element, is in fact exactly at the height 1/4 compared to the original element. In each of them are in the correct spot. So what is it that we got here? We got that this one block built this way, it produces different possibilities of embedding the path that goes from 0 to the top, right? I am in D2, so my path has length 4. So those are the options that I have, right? I put the top to be this element. I put the middle to be either H plus or A minus, right? So here I wrote H plus, and here I wrote H epsilon. Epsilon is either plus or minus 1. And then if I decided on H plus, then the bottom, I have two options, either H plus plus or H plus minus, right? I need to have a midpoint of this point, right? So here I'm writing epsilon and delta 1. Delta 1 is, and here on top I want to have H plus, but then a midpoint coming from the one that's not there, so that the point that I wrote over here has the set of coordinates contains the set of coordinates below, right? So I moved up by the height of this H minus minus by those extra things. And this is the exactly faithful embedding. And notice that this one block gave me what? 8 options, right? I can choose epsilon and delta 1 and delta 2 completely arbitrarily. So I have 8 options for embedding this one path, right? So that is, and they are well separated, each option from all the others. So now if I, in addition, introduce a big bunch of blocks doing this, it gives me the full embeddings of all the diamonds. And I do not wish to write the formula at this very rate. It's in the paper, by all means. Thank you.